Alright, welcome back. So in this video we're going to talk about an interesting phenomenon. This shape is actually referred to as Gabriel's horn, or other people call it Torricelli's trumpet. The basic idea is we take the graph of y equals 1 over x. We look at it in the interval from 1 to infinity. And we take that graph and revolve it about the x-axis to generate this infinite solid. Infinite solid. Now the name Gabriel's horn, or Torricelli's trumpet, is the other name that it gets, is this infinite, again, horn, right, that's infinitely long, right, and it goes out forever. Okay. Now, it gets its name from the Christian tradition, where the Archangel Gabriel blows the horn to announce Judgment Day. So that's kind of where the name eventually came from. The idea being that you have this infinitely long horn, so it's going to take a very long time for anything to come out of it. That's kind of the idea of the name. It's really interesting what we're going to discover about this solid here, this infinite solid. It was first studied by a guy called Evangelista Torricelli. And so he actually didn't call it Gabriel's horn. That was a name that was given to it later. So we're going to take a look at this. And what we want to look at is the volume of this horn, as well as the surface area of this horn. So we're actually going to use two of our results from the past as we take a look at this. So as we look here at Gabriel's horn. Okay. So first, let's talk about the volume of this solid. Okay, we weren't able to talk about this before because we didn't have infinite integrals. But now we can talk about these integrals as we go to infinity. So we approach the problem of volume. So let's talk about the volume. Remember, we have two options for volume. And in this case, the disk method is definitely the best approach. Since we can very easily measure perpendicular to the axis of rotation. All right, that's just going to be our function there. So the disk method works best for volume here. So as we approach the question of volume, we know that we're going to do the integral from a to b of pi times the function squared, the radius squared, dx. So in our case, we would be dealing with the integral from 1 to infinity of pi times 1 over x squared dx, which we can now, of course, write out as the limit as b goes to infinity of pi times the integral from 1 to b of x to the minus second dx. Okay, we can very easily work out this integral. Limit as b approaches infinity. Do the integral at 1 to it, which make it negative 1, divide by it. So we're actually going to have negative pi b to the minus 1, or negative pi over b, or negative pi over x, sorry, getting ahead of myself. And it's going to be evaluated between 1 and b. So we have the limit as b approaches infinity, and we evaluate that. Negative pi over b, and then that's going to be minus negative pi over 1, or just plus pi. And then we take the limit of that. And we turns out this horn has a volume that's just pi cubic units. Pi cubic units. So we have this infinite horn, and it actually has a finite volume. It actually has a finite volume. This infinite horn that actually has a finite volume, which is Well, quite frankly, that's pretty cool. That's pretty cool. This infinite horn has a finite volume. Pretty cool. Pretty cool idea. But that's not the cool part. It gets even cooler. Because let's now talk about the surface area of this object. Let's talk about the surface area. So recall that surface area of an object is the integral from a to b of 2 pi f of x times the square root of 1 plus the derivative squared dx. Okay, so let's take a look at that here, and we're going to try to work out this integral here. Okay, so first things first, f of x is just our 1 over x function, and f prime of x is the derivative of that. It should be negative 1 over x squared. Negative 1 over x squared. So we set up our integral. Limit as b goes to infinity of 2 pi integral from 1 to b of f of x, which is 1 over x, times the square root of 1 plus the derivative squared. So that's actually going to be 1 over x to the 4th. Okay. And we're going to go through and do a little bit of simplifying here. So I'm just going to work with the stuff on the inside for the time being. So 1 over x square root. All right, so here I would get a common denominator for the 1 and the 1 over x to the 4th. And it would actually make this x to the 4th plus 1 over x to the 4th. Now we're going from 1 to eventually infinity, but the important thing is everything's positive. So when I do square root here, right, that square root is going to apply to both parts. I'll have 1 over x times square root of x to the 4th plus 1. And then square root of x to the 4th would just be x squared. So all of this stuff simplifies to be the square root of x to the 4th plus 1 all over x cubed. Okay? So that takes our problem down to this point. Limit as b approaches infinity of 2 pi times the integral from 1 to b of the square root of x to the 4th plus 1 all over x cubed dx. And that gives us an integral that's, well, quite frankly, how do we proceed from there? How do we proceed from there? That presents a bit of a problem for us. Right? Quite frankly, that just presents a pretty big problem that we're faced with, and how do we address it? But we can actually make a little simplification here. Okay, we can actually make a little bit of a simplification. Because we know this. But we know this, that the square root of x to the 4th plus 1 over x cubed, okay, is greater than the square root of x to the 4th over x cubed. We know that this is true as long as x is greater than or equal to 1. Actually, it's true as long as x is greater than or equal to 0. But specifically, it's true when x is greater than or equal to 1, which is when we need it. Now, how does this help me? Well, here's how this helps me. That means that this function here is always going to be above this function. So I actually turn and consider the integral of this function. Okay, I consider the integral of this function. And then whatever answer I get for the integral of this second function, the integral of this other function has to be bigger than it. Okay. The integral for the second function has to be bigger than it. So I work this out and see what it gives me. So we consider that limit. Limit as b goes to infinity of 2 pi integral 1 to b of the square root of x to the fourth over x cubed dx. But the square root of x to the fourth, when x is greater than or equal to 1, or again when x is positive, square root of x fourth, just x squared. And then x squared over x cubed will just become 1 over x. And so we can work that integral out. Limit as b goes to infinity of 2 pi ln of x, evaluated between 1 and b. And that'll be the limit as b goes to infinity of 2 pi ln of b. Because ln of 1 will be 0, so the second term will subtract off and be nothing. But ln goes to infinity as b goes to infinity. And so that integral is infinite. So if that integral is infinite, and we know that this always has a bigger radius all the way through, bigger height all the way through, then we also know that the other integral has to be infinite. So the integral from 1 to infinity of 2 pi square root of x to the fourth plus 1 over x cubed dx also diverges. And so here is this amazingly strange result. This horn, this infinite horn, has a finite volume of pi, and an infinite surface area. Okay, so what a crazy shape. The volume inside is finite, but the surface area outside is infinite. So the simple statement is this horn would not be able to contain enough paint to actually paint the outside. Right? Paint the outside. Now, I've actually read, if you look up Gabriel's horn, they actually get into a more complicated discussion about that question of infinite paint. We don't want to get into that, but this idea that we used here, that I used here to get this result, since I have an integral here that I'm very much troubled at trying to work out. This is a result idea that we're going to use in upcoming chapters, this comparison idea. So I compared it to something else, which I know it's definitely always bigger than, right? Because of that plus 1. Right? It's always going to be slightly bigger. Not much, but enough. I can work out this integral. It's infinite. So therefore I know this integral has to also be infinite. By the way, if that first integral had been finite, that doesn't mean the next one would be finite. But because it's infinite, I know the other one has to be infinite. So that integral also diverges, meaning that this thing actually has infinite surface area, but a finite volume. Okay, so it's a really cool result there. We have this horn that actually, again, has an infinite surface area on the outside, but a finite volume on the inside.